What lies above and below the solar system? This is actually a side-on view of the solar system. Nearly all the planets orbit within the same flat plane, the ecliptic. But what if you wanted to fly out of that plane straight up or straight down? This is one of spaceflight's most celebrated unsolved challenges, the vertical escape problem. In 1958, American astrophysicist Eugene Parker discovered that the sun is far from a solitary self-contained ball of fire. Continuously blasts streams of charged particles outward in every direction. These high-speed particles inflate an ever-expanding bubble around the entire solar system, the heliosphere. Acts like a vast protective shell. Inside, the solar wind reigns. Outside lies true interstellar space. The catch is that the overwhelming majority of objects within this enormous structure are crowded into that same flat plane. In other words, nearly everything humanity has ever observed about the solar system has come from the vicinity of the ecliptic. We have, in essence, been trying to understand a three-dimensional structure through a two-dimensional lens. In 1959, American cosmic ray physicist John Simpson was the first to state the problem plainly. Humanity had to leave the ecliptic plane. Our understanding of the sun's magnetic field structure, the origins of the solar wind, and the propagation of cosmic rays was almost entirely drawn from observations near the solar equator. Simpson realized that if we could one day look down at the sun from above the solar system, we would for the first time truly understand how the solar wind is born, how solar magnetic reversals unfold, how galactic cosmic rays penetrate the heliosphere, and what the heliosphere's outer boundary actually looks like. That vision would eventually become the Ulysses mission. But scientists quickly ran into a brutal physical reality. In principle, a spacecraft can certainly fly perpendicular to the ecliptic, but in practice, getting there is extraordinarily difficult. Many people assume that since the solar system resembles a flat disk, simply flying straight up should be the easiest way out. The problem is angular momentum. Every spacecraft launched from Earth inherits Earth's orbital velocity, roughly 30 kilometers per second, directed sideways around the sun, heading to Mars. That inherited speed is your friend. A modest extra push puts you on an intercept trajectory. But to escape the ecliptic plane, that sideways velocity becomes your enemy. Your destination is up, but your momentum is sideways. The spacecraft must cancel its lateral velocity and simultaneously build vertical velocity from scratch. Vertical escape is, at its core, a fight against the enormous angular momentum baked into the solar system at its formation. Even so, engineers refused to give up. In 1918, Soviet spaceflight theorist Yuri Kondratyuk proposed that spacecraft could borrow speed from massive bodies using their gravitational fields, what we now call the gravitational slingshot or gravity assist. In 1929, German rocket pioneer Hermann Oberth described what became known as the Oberth effect, a spacecraft that first plunges deep into the sun's gravitational well and fires its engine at the closest point, where it is moving fastest, gains a disproportionately large boost in orbital energy. The faster you are already moving, the more energy the same quantity of fuel can deliver. Together, these two ideas laid the theoretical groundwork for any realistic vertical escape mission. In 1977, NASA and the European Space Agency formally approved the International Solar Polar Mission, later renamed Ulysses. It was humanity's first genuine attempt to break free of the ecliptic. Given the technology of the era, Ulysses did not dive toward the sun for an Oberth maneuver. Instead, it flew out to Jupiter and used the giant planet's gravity to wrench its orbit into a steep inclination. Ulysses ultimately achieved an orbital tilt of nearly 80 degrees, and for the first time, humanity observed the sun from above the ecliptic plane. The results were striking. The solar polar regions turned out to be an entirely different environment from the equatorial plane. There, the solar wind screamed outward at 700 to 800 kilometers per second, nearly double the 400 kilometers per second slow solar wind near the equator, and it was far more steady and uniform. More remarkable still, Ulysses detected large quantities of dust streaming in from interstellar space, entering the solar system through its polar regions. The poles of the solar system, it seemed, might serve as the primary conduit for the exchange of material between our solar system and the rest of the galaxy. Yet, even Ulysses left the biggest question unanswered. What does the heliosphere actually look like? For decades, scientists imagined it resembling a comet, smooth on the sunward face, with a long trailing tail, shaped by the solar system's motion through the interstellar medium. Then in 2020, a team at Boston University proposed something radically different. They found that the heliosphere might not look like a comet at all, but more like a collapsed croissant, bulging in the middle, with two lobes curling backward along the magnetic field lines, and possibly no traditional tail structure whatsoever. The model unsettled many astronomers. But it cannot yet be confirmed. For a simple and frustrating reason, virtually every spacecraft humanity has ever sent, including Voyager 1, has crossed the heliosphere by traveling laterally through the ecliptic plane. We have skimmed past the heliosphere's edge. We have never looked down on it from above. Even Ulysses, the closest humanity has come to a vertical escape, traveled no more than 800 million kilometers above the ecliptic. The true boundary of the heliosphere may lie 18 billion kilometers out. We haven't even covered a 50th of the distance. Truly vertical deep space mission remains, to this day, beyond our reach. In 2018, the Applied Physics Laboratory at Johns Hopkins University hosted the Interstellar Probe Exploration Workshop, where researchers for the first time systematically proposed combining a solar orbit maneuver with a large solar sail to achieve a genuine high-inclination escape from the solar system. In 2021, NASA allocated $10 million to study the mission's orbital design, technical feasibility, and scientific objectives. If the program moves forward on schedule, the optimal launch window falls between 2036 and 2041. The spacecraft would take roughly 25 years to reach the edge of the heliosphere, and for the first time, humanity would look down on the solar system as a whole. We would see the vast disk of planets wheeling around the sun. We would see the dust lanes suspended in the ecliptic plane. We would see the heliosphere wrapped around it all like a cocoon, and we might finally begin to understand our solar system's true place within the Milky Way. Humanity has already photographed a black hole. We have imaged the galactic center. We have peered back to the universe's infancy, capturing the first galaxies and the afterglow of the Big Bang. But there is one photograph we still do not have, a bird's-eye view of our own solar system. And that, perhaps, is the deepest reason to break free of the ecliptic.